Okay, we're going to do something different today. No lecturing. I call this fun. But we are introductions. I find that it's often helpful to with introductions to sort of get some practice doing them. And I have also found that when you start actually doing them, you start realizing all kinds of things that it didn't occur to you to ask about it, because when I do it, it seems so seamless and awesome. So what I want you to form into little groups. I don't think you should do it alone. So make yourself into groups of 4, 3, or whatever. But I will actually give you the best hint of the book. I will tell you what I want you to reduce from, which is usually the hardest thing to do. So the problems that are really one. The left-hand side, the problems are sure to be it. I'm technically not showing that everything very well because unless I know all the problems on the right are. But what I want you to do is take the problem on the left, so hitting set, which is very clearly there, and show that it's reduce to it from the problem on the left, which in this case is vertex coverage, which actually knows it. So usually you have this, you don't have that, and you go through some catalog of problems that are actually helping you here. So it's so much easier now. Okay. Actually, 6 of them I've only given. I want to get you all distracted. So I suggest for now, just for the first 5-10 minutes or so, just look at the first one. Prove that it is complete using vertex cover. I will walk around and take questions from you. For this screen, actually. So think of the universe as 1 through 10, and S1 could be 1, 1, 2, 3, 4, 5, 6, 7, 8. How are things going? Does anyone have any questions so far? That yes no question, the that yes no question. Yes, that means that the answer is the standpoint.
It's asking if there is one. It's not empty. Now, suppose H had to be really small. K, H could be no bigger than this. That H around so that it touches. My birthday is as an example.
So let's take a brief stop. Since, as far as I can tell, that actually sold the problem yet. You probably have questions and ideas and problems to solve yourself. Okay. So, any questions so far about where things are? Are you more or less figuring out what needs to be done? You've done it, but you have a sense of what needs to be done. What things are people getting stuck on right now? Any thoughts? I can assure you that if you're getting stuck on something, probably half the other people are getting stuck with us. So feel no shame. Yes.
So I know that when I'm trying to reduce vertex cover to dictating set, the set that I'm interested in, the set of vertices, which can be of the size A. Then I'm trying to relate that set H.
Correct. That's what you want to do.
That's what we do.
Yes. Okay.
And it seems like the edges in the graph needs to be related to the power set,
The collection.
the set of the collections.
Yes. That's also a good observation.
Yes. But I'm not finding the relation.
You're about like 99% of the. The last 1% is very long. It's like Microsoft. Yes.
So if I take the edges in the graph as subsets S1, S2, Sn.
So the edges are subsets. Then if an edge is a subset, what are the elements of? So the first question is, okay, what do you think the universe U should consist of? So does everyone agree that the universe U should consist of vertices?
Yes.
Why do you think the universe U should consist of vertices?
Because the Higgs set algorithm will find a subset of U
Okay,
is at most size K.
right?
Seems,
It seems like that's what you want.
yeah.
Okay, and I'm not saying this is right or wrong, but it's a good first place to start. That I want to find a set of size K, I want to find an H of size K, so probably H looks like vertices. Well, if H are vertices, then U should be a set of vertices. Good. If the universe is a set of vertices, what will the edges then correspond to? This is what Nitin said. It seems like the edges would have to be sides, right? How is an edge is an edge? A subset is a subset of the universe. How is an edge a subset of the universe of vertices?
Have each subset contain vertices that have edges to each other?
No, I give you an edge.
Oh.
How do I express this as a subset of the universe H? Or universe U?
A pair of vertices.
A pair of vertices, the two that are endpoint. Okay, so now we have a construction. We said, okay, the universe U is going to be the set of vertices. Subsets are going to be one per edge, maybe? Is that what you're thinking? One per edge, and each edge is going to be a pair of vertices corresponding to that vertex. So, M, you have subsets, one for each edge. Now what? So you have a construction. You have an instance. You have taken an instance of vertex cover apart from the parameter k, and you could convert it an instance of hitting set again apart from the parameter k. But based on what you said, the same k is going to be copied over there because you are thinking vertices here, hitting set here. Okay. So now I have a correct instance. So you have the mapping that goes from instance to instance. What you need to do now is improve this equivalence. Right? So often the first step in this process is to construct the instance. So you construct the instance and okay, it looks plausible. Can you prove anything with it? So now the question, what do you have to prove? What are the two things you have to prove? Anyone? Yeah?
I have a question.
Okay, good.
When you say collection is subsets of U, then is it all possible subsets of U?
Did I say it's all subsets? Alright. So what do we have to prove? Right? What do you have to prove? What are the two things you need to show?
Forward and backward. Right?
Okay, what's forward and back? What's backward? What does he think we need?
So,
If S intersect
if
if S intersect H is the empty set, then we have a minimum cover, and if we have a minimum cover, then we have some H that will enter
The
them.
second sentence I agree with. The first sentence I'm not sure why you're talking about intersection H. You're almost correct. What you're trying to say is the following. If there is a hitting set of size K, where the hitting set means whatever properties it's supposed to mean, then there is a vertex cover of size K. And the second statement is, if there is a vertex cover of size K, then there is a set of size K. Right? At most in all cases. Okay, so now if we have to prove this, let's take one of these statements. If there is a hitting set of size at most K, then there is a vertex size at most K. Okay, so let's call our oracle. We compute the hitting set of size at K. Can you convert this into a vertex cover? First of all, mechanically, how do you convert this into a vertex cover? We're claiming, you just take all the elements H, there's one for each vertex, pick those vertices the instance was telling us to do. Okay, is it correct? Is it a vertex cover? So clearly, is it a vertex cover? Does it cover all the edges? Again, proof by contradiction. Suppose there's an edge that does not touch, right? That does not incident on. That means that both elements of that edge have not been picked to be my vertex cover. Right? Therefore, both elements of that edge, their corresponding elements in U were not picked to be in the hitting set. Okay? Can this be a hitting set? Because there's a corresponding edge subset in the hitting set problem that had to have been hit. That intersection had to be, had to be non-empty. You had to pick all these two things. That's not possible. Therefore, this can't happen. Therefore, hitting set you do know. That makes sense? Yeah.
Can I assume you think that it's mapped to more than one two edges? Like this one be a set of 4 vertices.
S1 should be set of 4 vertices. We have full control over what S1 looks like. We have no control over what the graph looks like. Remember, our mapping is going from the graph to a very instance of the hitting set problem. We have full control over it. We're not looking at a general hitting set instance. We only have used two element subsets. Make sense? Okay. So we proved the first part of the statement, that the hitting set implies a vertex cover. What about the other way? Can we now do the other way? Very similar reasonings would apply. Suppose you have a vertex cover. Do you have a hitting set? Well, not. Assume that you don't have a hitting set. The corresponding set of elements here for that vertex cover there were my hitting set. Then what happens? It's not a hitting set. Some set does not get hit. If some set does not get hit, that corresponding edge did not get hit. But we just said there was a vertex cover. It's not possible. So we have a contradiction. And so both sides imply with the other. The reduction runs in linear time. Right?
Do you have to prove that?
Yes.
How would you prove that?
You tell me the reduction. The reduction is what? Take the vertex and write it down as given ID. Take every edge, write down as a pair of elements in a set. How long does it take to do this?
Just 1 to 1.
Just read the whole thing through, so it's linear time. But that's important. If you don't do that, then you don't know all of them. In this case, it's kind of obvious, but you still see it. Because if the reduction does not fall under the time, you don't know proof of NPR. Because the reduction takes exponential time, you don't know proof of NPR. So you have to say it runs in the problem. It doesn't matter what problem it is, but that's square root improvement. I don't care. And the proof doesn't care. But it has to be polynomial.
Okay, so I can recognize that it would be convenient if it were polynomial.
No.
But you,
It's
you
not-
made,
it's
you made
it
a
must.
stronger statement.
It's must.
Why?
Why? Because for me to say, remember the whole hard easy thing? I'm saying, okay, I'm going to solve P using Q. If Q was easy, P would be easy, and that's not possible because I know P is hard. That's my argument. The whole statement was, if I could solve Q, if Q was easy, P was easy, is only true if the mapping to get to Q was also easy. That's why it's important. Got it? Very good. Okay, this is a good question. We have to. This is very important as well. And of course, it doesn't matter what kind of problem. Because we're defining easy problem. It's not for student practice, but for the purpose of complexity, it's all up there. Okay. All right. Does this make sense? This first problem? Yeah. Ready to do another one? Okay. So the next one we're going to do. Let me see. I don't want to give you. So the one that I originally thought was the first problem is actually quite hard. So where's my first one? Let's see. See, this is not so bad. Try this one. From prove that dominating set is incomplete using again our old friend vertex cover. And first, make sure you understand the dominating set problem before you do anything else. It's a little, just like people. So take your time. Just read this. Does the problem definition make sense? Any questions on the problem? So there's two parts, right? A set is a domain set if it's, if every vertex is either in the set or is close to the set. The kind of influential element. They're within one of every vertex. Okay, if you understand the problem definition, start production. Yeah.
This is the exact same question.
Is it?
I'm missing something.
Are you saying that anything said is the same thing as dominating set, or are you saying the reduction is the same reduction?
I'm saying it seems like the exact same thing. Dominating set is the same thing as the vertex cover.
Okay, then forward. Well, I see. You're saying, well, no, because good. They're not the same problem. In the vertex problem, you're covering edges. In the dominating set problem, you're covering vertices. I could cover a vertex without covering any of the edges nearby. Right? So it might help you to draw an example. Try to play some examples under the assumption that they're in fact different. Let's see how you could make the solution to dominating set different. So this is a good exercise to do before you think, because it helps you understand what dominating set is. Try to make a simple example. Three or four words, like a star. Try to play some example. See what the vertex cover solution like dominating set. And I can assure you that you can find an example. Just draw some examples. Yeah, I should mention this is a good point. So we had a question, right? They seem like the same problem. I don't know if any of you had the same feeling. I've had the same feeling many times when I first looked. I was like, they seem exactly the same. And every time I show this problem in class, people insist that they're exactly the same problem. So they're not, but they look very similar. And it's good. It'd be a good idea to try some simple graphs, see where they would actually give you different answers, where they could give you different answers. So it's a good thing to do, not just because you want to do the reduction, but because it gives you a better sense of what dominating set is all about. Right? And you need that understanding of the constructive reduction. Okay? So it's a good practice. This one way I think what is cover you're covering edges, and dominating set you're covering that. And that can make a difference, especially make a difference that you have high degree rules.
Yeah, what?
High degree. Then there's a big difference in edges being covered in what is so that's the intuition. So yes.
Why is it that we would have something
So, for example, Were they different? Okay, good. So you're satisfied they are. If I said, but if you did that, I mean, I should say this one is a little trickier than the previous one. That one is kind of the thing that you need to do, you did. Here's a little bit more complicated. It's not hard, it's a one-line story. Yeah.
But a good place to start would be to try and promote every vertice is dominated set. Has to be
Just asked him, he said they're
well, trying to prove that
You got to be careful with this. You can have wonderful what you have to prove is that there exists that contains the that's what it's supposed to be doing.
so that every vertex has an offset. Finding the subset, finding the dominating set, and seeing the versus dominating. Okay, so you can't do
If any of you are already done with this, I'm not saying you should be, but if you are, you can go on to the next one.
right, so maybe I'm not worried about it. All you need is that here.
Okay, so again, this is one of those cases where it seems like it should be easy. Your instance of the vertex covers a graph and a parameter k. Your instance domination is a graph and a parameter k. So the transformation will be trivial. Is it?
No,
Why not?
because I found a counterexample where that was.
What the counterexample is. So I mean, not what it is, but what does it tell you? What is it saying that you're talking about?
For example, was saying that you could have a smaller 180 set than a vertex cover.
So the counterexample you are producing that for the same graph, it is possible to have a smaller developing set than the vertex cover. Why is this a bad thing?
It's not macro now. That would have macro more problems for that.
And you, in particular, if you took the key here, you couldn't do it. Is it always smaller by the same amount, thing, or is it not? Or could it be different? Like, could it be that, oh, it's always half the size, so I can convert K to K over 2? Does that make sense or not clear? Okay. So the obvious transformation has a problem. The problem is that they're not the same size. It's not clear where you can fix this problem by changing the parameter. Maybe you can, maybe you can't. So now you have two options. You can either change the way you map the instances, or you can think about this K thing. What do we think? Where have we gone so far?
Change versus to edges, right? Versus to edges, edges versus.
So your idea was to change vertices to edges and edges to vertices. So how do you do that?
We have a lot of duplicate.
No, how do you change vertices to edges and edges to vertices?
If there are there's a vertex between two edges.
Sorry, that's you.
What? Imagine A, B, C. And
Oh, this way. Okay, so yeah, okay.
Yeah. And if I have H1, H2, then I would put a vertex between. I would put an edge between lines and getting. Let's call vertices 1, 2, 3, and edges A and B. Yeah.
No fancy math. So yeah, no, you're talking about the line graph. So continue your argument.
Okay. So the idea is when I use A and B as vertices,
Yes.
and since I have a vertex now, I'll put an edge between A and B.
So the idea is each vertex in the original graph becomes a vertex of this new graph.
It will become more than that, because the vertex can have more than vertices.
Oh, so you make multiple copies of this thing.
I mean, that's how we have to do it. I mean, I don't have to.
So for each pair, you'll sort of lower the by a factor square. Oh, this is even more interesting. So, first I learned a bit of technical wizardry to get this into the drawing. Let me see if I can. So what you okay? So if you didn't do what you said, if you, by the way, just as a separate note, as Chris was saying, if you say that okay, every edge in my graph becomes a vertex in this new graph, and I connect two vertices in this new graph, which are edges in the new graph, if they share a vertex in the new graph, that's called the line graph of a graph. It's a well-known concept in graph theory, and it has some nice properties. So that's something that's good to know. Having said that, let me attempt to do something. So let us draw some things out. Ooh, I have a solution. I don't want to see that. Okay. So I think the argument here was something like this. Yes? So you would make what a new vertex AB. Is that right?
Vertices will be A, B, C.
The vertex will be ABC. Okay. And now we're
Now, 4 will have connection between A and B is 4. The edge name is 4.
what's it?
Yeah.
What about B and C?
B and C will 4 again.
So you're getting rid of hypergraph. Okay. Okay, but does this help?
Yeah.
You can prove it?
No.
So wait, what is the definition of help?
So I was thinking what other ideas there, like we're stuck here.
Okay, any other thoughts on how you might do this as a reduction? So clearly just taking G and copying it was not working. Now we're trying to find some more creative solutions. This is one. Another one, the one I was telling you, would be to create a line graph, which would look like this. So you'd have one, again, edge for everything, and in fact, it would just look like the same thing. It would just be a line graph. This is called the line graph.
But how do you base the edges on?
So if the G is V comma E, the line graph of G has vertex set V prime is equal to E, and there is an edge E1, E2 belongs to E of L of G if E1 and E2 share an edge point. Because even E2 are edges vertical. So that will essentially every vertical degree K becomes a completely precise K. Yeah. So for example, if you had this in my original graph, it would become but okay. I don't know if the line graph is going to help you, but the problem is I know, and I'm not sure, I don't know if this sounds really helpful. What, can you say anything about the vertex cover in a line graph? So here's the problem with the line graph type argument, right, or these kinds of arguments. The vertex cover, which is a set of vertices, will now become a set of edges in this construction. But I want the vertices in my output. Because the domain is also a set of vertices. So arguing that transform vertices into edges and edges to vertices have the problem that now the thing that used to be a vertex is now an edge. The thing that used to be an edge is now a vertex. I'm finding vertices here, but there are edges here, so I have to find some way to map them back to vertices here. And that gets tricky. I'm not saying you can't do it, but it gets hard now.
But even here you don't have all the edges mapped to words, or you have all the edges mapped to words, but all the words are not mapped to edges.
No, that maps some other stuff. Yeah. I mean, there is a notion of a graph duality, but graph duality has involves things like cycles and stuff. It gets a bit more complicated. The line graph is not technically a graph dual, because the line graph and line graph are not a graph, not the original graph. Any other thoughts? Yes.
Just from the one simple example, like it seems like there's some kind of inverse relationship between what's in the cover and what's out of the cover. That what's out of the cover kind of maps nicely to the dominating set.
Like the independent set that we saw last time? That the complement the vertex cover was somehow interesting?
Yeah.
So can you formulate a conjecture that could be proved or disproved? Are you saying that the complement of a vertex cover dominates that?
Yes.
Well, at least the,
Yes.
the number of elements. Yes.
You are.
Yes.
You don't appreciate it, and you read back there. So the claim on the table is good to have claims on the table, because we can prove them or disprove them. That, okay, there's a strong and a weak version, I guess, right? So the strong version is that complement of vertex cover is a dominating set. And the weaker case is that the number of vertices in the dominating set is equal to n minus number of vertices in the vertex cover. So this is a complement. So this is a very concrete claim. That's good. You can prove it or disprove it. Anyone want to take a hack at either of these things? I mean, if you could prove this, would be done. But we know that a complement of vertex cover is an independent set. So the strong version claim says an independent set is a dominating set.
Which I think is true.
Which you think is true. So prove it.
So, if, so if the independent set wasn't a dominating set, then there would be a vertex that's 2 hops away from everything in the independent set or more. So that means that you have that vertex that's 2 hops away to the independent set. It would be independent set. Well, it would be a
This is the claim. And the claim is that if the well, I guess you're getting a maximum independent set.
Yeah, so that's probably,
Or actually you claim maximal independent set.
yeah.
Every maximal independent set is dominating.
Right.
Well, no. I think you're taking the opposite. Every dominating set is a maximal independent set.
No, I mean that every maximal independent set is dominating.
Okay, so let's say this is not dominating. Then, if not, there exists some vertex that's 2 hops
Or more.
away
Yeah.
from I. Okay? So let's say the path from I to V is like this. You have I here, then you have something here, it's called a W, then you have V. Right? And then your claim is that then I union V is also independent.
Right.
Okay, good. So this is part is correct. What about the other part? The other claim is every dominating set.
Yeah, that's not true.
Not true? You want an example?
You could just take, all of the vertices, and that would be a dominating set.
That's correct. Every dominating set is not maximum independent. You could take everything into your graph. That's a valid dominating set, but it's not maximum. So that so this claim is no longer true. So now,
Can we start from the initial problem and then go have a vertex cover?
but you don't have what you're constructing. You're not construct the reduction yet. You can't reason why you get. So not construct the mapping.
So my
Yeah, go ahead. Go ahead.
so logically I should do both ways, right? I can do one for
No, the reduction is one way. The proof is two ways. The reduction is one way.
so from the dominating set to vertex.
No. You take an arbitrary instance of vertex cover and you convert it into an instance that you claim solve the dominating set with vertex.
In the arbitrary set of vertex covers, I add extra edges, and all the vertices going to new vertices which are not getting quite.
Okay, so what you're saying is, okay, so you have a graph. What do I do now?
I just draw edges outside, make new vertices now. For each vertices, I just make extra vertices, and then do. Now, if I have a domination,
You said there are extra edges.
no, they're not just not mapping together. Yes.
Okay.
You can't link it back.
Why not?
I'm making the extra statements on the top, right?
Fair. Okay, sorry. No hearing video.
Now, if I do a down,
I just distracted you now, right?
if I do the domination set on this,
Yeah.
then I get all the internal words.
You will?
Yeah.
Why? Oh, you've added one from every single thing?
If I solve the domination set,
No, what I'm saying is you've added from everything?
yes.
Oh, I know that.
Yeah, and now if I solve the domination on this one,
Yeah.
I have all the internal vertices, and I might have some few outcomes too, which I don't care because I didn't know what they are.
Okay.
And if I take the
But how do you get the vertex cover out of this now?
that is solution of vertex cover, right?
But you just said you pick every single vertex in the internal graph for your dominating set.
No.
You just said that.
I solved the domination set on this.
On this graph.
Yes.
So now, but you, as you observe, in order to solve the dominating set from this graph, you will have to pick every single internal vertex.
Yes. And that vertex is covered, right?
Why?
Oh.
Suppose my vertex cover was this. My original graph was this. See a problem? Or the cat? But it's a thought. It's a good thought. I mean, so here's another idea. Take my graph, and now I have every edge. Okay. And what I'm going to do is, I'm going to replace this by this. For every edge in the graph.
On the side where it's still UV, or are you doing anything with the two on the side?
No, I don't know.
Labeled B and B, technically.
Yes. So in particular, if I work on the look graph, my claim is that I'm going to do this. Now what?
Was the dominating set problem looking up for the dominating set of the sizes at most cases?
Well, there are two different cases. You can choose changing the parameter if you want, right? Yes, but for yes, dominant set, some parameter, fixed parameter,
There's a bound.
some number you want to see, yeah, because of, as you pointed out, like you always take everything, so you want to make it as small as possible. I'm going to claim that this is sufficient, and in fact, I think the value of k is the same. Let me argue what I think is the easier side of this, that if I have a vertex cover of size k, then I have a dominating set of size k.
But if you pick all of the central vertices,
I know. I said if I have a vertex cover of size k.
vertex cover of this.
Suppose I have a vertex cover of size k. Right? In this case, what is the vertex cover of B? There's a vertex cover of size 2, right? That's I pick C and B. Yeah? That's a vertex cover. That's minimal. And I can do the same thing here. Wait, that's not dominating set. Maybe I need to make a different claim.
So isn't it just C by itself, the vertex cover, the minimum vertex cover?
No, because the edge AB is not covered by C. Look at the edge AB.
Dominating set in the first graph.
Sorry?
C is the dominating set in the first graph.
Oh, no, sorry. Don't say in the first row. I mean, the vertex cover first. Yeah, that's right. C is a dominating set in the first row. So maybe that was part of the yeah. Okay, so this is I'm not sure. Let me think for a second.
I think you have to do a vertex cover on that subgraph, the second graph.
I can't. I'm not. That's not what I'm doing. I'm completing a dominating set in the second row. My reduction is going from, it's one direction. I think I'm doing it a little bit different here. Let me just think for a second. I think my transformation is wrong. Let me try a different transformation. This is one. This is failed. Let's try two. This has been before, okay? But now I change my graph. So now this goes to, in fact, this. graph work?
Yeah, how it goes.
Good work for those example, that would be dominating set.
So is BC in fact dominating set of the 6? So I claim that now BC should be a dominating set, is it?
Yeah.
It works with So this I try to for my reduction. Does this work? So my claimed reduction now is take every edge in the graph and replace it by this transformation of there, where you add a new vertex for that edge and then make a little triangle. So again, let's try to prove this. Suppose the vertex cover in the graph. My claim is that that same set is a dominating set in the new graph. Right? Well, if that's not true, right? So let's say that there was some vertex in the new graph that is not either in the set or right? So there's some vertex in the graph again. So there's some vertex B, so there's at least one hop, and then at least one more hop to something that's in the vertex cover. So what's going to go wrong here?
So that would mean that that edge from W to X is not covered.
Well, X, W to X is covered because X was picked. X is my, B is the problematic one.
Oh, okay.
B is the one that's not covered. So then the edge from B to W
Yeah, that would not.
is not being covered in the vertex cover, right? So the claim is that if there is a vertex B not dominated, then it must be 2 hops away from anything that is in the set. Therefore, it has at least one edge to something that's not in the set. And neither of these two things have been picked. So this couldn't have been a vertex cover in the first place. So this can't happen.
Can I do it even if I take out the edge between A and AB and A and BAC?
Sorry?
Can I do the edge between AC and A and AB?
By the way, notice that I have not used this construction yet. This is actually just it seems to be a basic property of the domain set. I have not used anything at all. I have not used any extra edges yet. It's the other direction we're going to need. Suppose I have a dominating set in this graph. Can I extract a vertex cover from it? Right. So, any of these triangles can be covered by any of those 3 things. So the question is going to be now, how do you prove this? So we want to say that if there's a dominating set in this modified graph, then there must be a vertex cover in the original graph. It may not be the exact same thing, we can construct it from that. How do we prove that? If it's true.
You can pick a dominant set in this. Can I pick a dominant set anything I want?
Yeah, you don't know what somebody's doing. Pick anything. You could pick spurious vertices as well as real vertices.
Then if I pick AB, AC, and CD and DC.
That's not minimum. It's telling you, you're asking for a dominant set of size. Well, in 2 in this case, whatever, in K it is. So let's say pick some set of size K. Yeah. But I think your example is still good. So let's say it picks, it picks this one and this one and this one. Well, it's not well defined, right? I don't. These seem sort of natural vertices.
But yes, I'm starting from this graph, right? I get to pick this one.
Yes, but here's what I'm going to do. Okay, here's my claim. If there's a dominating set in the origin in this new graph, then it consists of real vertices and fake vertices.
Okay.
Carry all the real vertices over. For every fake vertex,
There should be
pick any of the 2 edges.
pick the. I think you have to pick the vertex which is not in the set.
Doesn't matter.
If it's already picked,
Then there'll be at most table. I'll only reduce the size of the vertex. So the claim on the table now is that if we already proved that a vertex cover implies a vertex cover size K will in fact give you a dominating set of size at most K. Without proving that if there's a dominating set of size k, then you look at the dominating set produced, keep all the real vertices for each fake vertex by one of the two real vertices that it must be connected to by this construction. And that is in fact a vertex cover in the original. Okay? So let's say, suppose this is not true, then there is some edge in the original graph that is not covered. None of its endpoints are picked. Okay? Now we know that this turns into this in the modified graph. That's how we do the construction. So if we're saying that none of the points are picked, that means we're saying that none of these three things are picked in the dominating set. But that means my dominating set cannot touch this. Because it didn't pick this, it's 2 hops away. So if there's a dominating set and I do this modification to the output, I must get a vertex cover size at most k. It won't be the exact same size as you pointed out. I mean, I could reduce the size. But all I'm saying is that the dominating set size at most k gives you a vertex cover size at most k. It doesn't have to be the exact same amount. So that's a proof. So again, reduction is not hard to define once you see it. And the proof takes a little bit more effort. And notice that we needed the special trick for the second half of the reduction. The first half just kind of followed through anyway.
Can you formally write steps?
Yeah. So let me write the steps. So now that I know what I'm doing, right? Yeah. So now that I know what I'm doing, I can actually write the proof. So okay, this is my construction. This construction runs in linear time. Because I'm doing something for every edge, for every vertex. Okay? This data structuring stuff there. Again, as long as it runs in column time, you don't really care what you do. It's at most n squared, whatever. So now the claim one. Okay. Okay? So this is part of the proof. Suppose we want to show that the vertex cover of size k equals the dominating set of size k. Given some subset of size k that is in fact the vertex cover, set the dominating set to be exactly that set. Because we got the mapping here, all the vertices of V are included in the V prime, so we can do that. Suppose it's not a dominating set, then there must be some vertex that has 2 hops from the dominating set. So it must look like V connected to W connected to X, but X is a dominating set and V and W. But then V and W is not covered. The edge VW is not covered by the vertex contradiction. This is the proof we just outlined. Yes? Make sense? Okay.
What's wrong? So the vertex cover is the graph G, and then you map it to DY. This both proof you're talking about is on the same graph.
No.
After the map.
Yeah, after the mapping. So I have the original vertex cover with the graph for the graph for the wings as well. That construction tells you how to get G prime from G. Because I told you how to write on B prime, I told you how to write on G prime.
So you have a solution for vertex covering G, and now you are using that to come to a solution for domination matrix.
Domination
prime.
in G prime, yes.
In G prime.
Yes, absolutely. Correct. Okay, so that's one thing. Then the second claim.
One thing I would say though is that W wouldn't necessarily be in the original graph, right? Or V or W would not necessarily be a vertex in the original.
Good point. So, to do two cases, very good. This is not a complete proof, right? So, okay. So let's draw the picture then, right? So remember though that by our construction, okay, good. So let's think about this for a second. So the problem is W might not be part of the original graph. So maybe I don't care about the edge W. So let's see. So when would this happen? This would mean that V is connected to some fake vertex and is connected to some X that belongs to the dominating set. But if V is a fake vertex, also must be connected to some real vertex, which is also connected to the dominating set. Right? And similarly, this fake vertex is connected to X. It's also connected to something else. It's connected to something there. So then this edge, which is a real edge in the original graph, is not covered. Because, okay, here's the argument, right? I take my vertex cover, I put it over, so this is my dominating set. V is not part of the dominating set, so there's 2 hops away. If it's 2 hops away through a vertex of the original graph, then we're done. That contradiction holds. We have the argument I just wrote down earlier. If our 2 hops away holds through a spurious vertex of this kind, then we draw this picture, we can complete it in this manner.
Well, actually, the first one, if W is a vertex in the original graph, the edge connecting W to X would be in the original graph, but the edge connecting W to V may not necessarily be if V is a vertex.
Good, that's another case you discussed. And I'm glad you picked this up, because it's still okay with this. But so let's take the case when V is in fact a vertex of the original graph. And either that case holds, or this case holds, or this case again this edge is not covered. So let's get to the second case now, when V is in fact a spurious vertex. So now we have a picture that looks like this. We have a spurious vertex, right? Which we know is connected to, which is 2 hops, which is connected to the dominating set, the claimed dominating set. Now, no spurious vertex is connected to any other spurious vertex. So the things it's connected to look like this. We know this is not in the dominating set, otherwise we'd be done. So therefore, this edge is not covered. So I brought this up. We have to argue this more carefully and just screw it out. Thankfully, it all works. But you're right. This is all it. So good. So in fact, basically, claim 1 also uses the special construction of the behind it. It's using it in a very careful way. Good. Very good. Thank you. So claim 2 was the converse. So it said that a dominating set of size less than k implies a vertex cover of size less than k. And the construction is, so assume some dom of size k. It consists of 2 sets of vertices. We'll call them real and fake. Okay. So I add R to the vertex cover, and for each UV belonging to the fake set, add either U or V to the vertex cover. Okay? So, number 1, the vertex cover is less than equal to the size of the dominating set, which is equal to A. So the size is correct, because I may add something new or not, but I never added anything that wasn't dominant. And suppose BC is not a cover, then there is some, let's call it A, B, that is not covered. If AB is not covered, then in the dominating set graph, the picture looks like this: side A, side B, side AB. And by construction, the dominating set did not pick A, others have put it in. It did not pick B, others have put it in. And it did not pick AB, because others have put it in. So none of these things are covered. Therefore, AB is 2 hops from anything, from DOM, contradiction. Actually, it could be a simple one. And we're done. So again, a long proof, but could line. You have to do that job. Yes.
I'm confused to understand the reason the Ks are different, especially if we're proving the economic.
In general, the Ks would be different. What I'm saying is that this particular reduction would be the same value. So K is a parameter of the problem. I can play like I did with vertex cover independent set. I said K begins minus K. Here I'm actually use the same K throughout. Choosing to use the same K throughout, I didn't have to, but I'm going to. That's all. That's all.
That's the only reason why you wouldn't use the same K.
Always. Well, for vertex cover independent set, I can come up with it. I use the K minus because one is minimizing, one is maximum. If one becomes small, the other becomes big. So I had to change it. And then other one. If I change the size of the graph, for example, I might have there's some reduction in the size of the graph, then a vertex cover size K in this graph becomes a vertex size K squared in the next graph. We'll actually see some examples of this in the next few lectures. Does that make sense? So we had the reduction, we had the forward direction, we had the backward. That's always every NPR analysis proof is all about. The first, the magic step, which I sort of saved you from, was how do you pick the problem to start? That's very hard. So normally in practice we all have a little dictionary of 5 or 6 problems that seem to work. If your problem looks like this, use this kind of problem. If your problem looks like all little fills, you use 3 SAT, which is horrible and we do 10-page proofs. But if you grudge it enough, you can make it work. So we don't actually look at all 3,000, 4,000 problems in 5. You have to be much clever. This is what the clever is. Once you have that, then you're in this realm, and now you what my reduction look like, what should it look like, let me construct a try, okay, this is the third, okay, this is move, or go back and do another try, and you go back and forth until you get it. Like any proof. Never get the first one. Any questions? No? All good? Yes?
So because the transformation early from the graph to the hypergraph where you inverted the nodes of the vertices and edges wasn't polynomial transformation, it wouldn't have worked out to be a valid.
Okay.
Well, would have been too complicated to create a reduction out of it, and that's.
You could try. I just didn't see it. Because semantically I was converting vertices to edges, which I didn't want to do because I wanted to keep vertices as vertices. So I didn't know how to make that work. So I felt uneasy about it. So I said, okay, maybe there's a better way to do this. Right? I didn't have a complex that wouldn't work. It just didn't feel right. So these things are ultimately about intuition. But maybe you could have. But yes, if you could show that it was going to be experimental, then I'll be back. That was not an issue. I think complexity would be because you blow something up to D to something of size D squared, and then so some of the squared. You get it. Any other questions? So do you feel like you have a little bit of a better handle on what the mechanics of reduction is? Hopefully at this point you know why we need to do these reductions to show hardness. But the whole point today was showing the mechanics of the process, not so much the high level. So hopefully with these examples, and the page I put on Canvas has more. So they're fun to try out. Other examples you could work on as well. I was thinking of it, so fine. They all work the same way. All the cleverness comes in, like I said, with the first step, which one we pick to start. and then how you build the reduction. And it's always a good practice to build an explicit reduction first, even if you don't think it's right. Because once you build it, then you can prove something. And once you fail to prove it, find an example wrong with this reduction. I need to change it. But if you're just kind of thinking at all these levels at the same time, how to prove it, it gets very confusing. So always try to come up with something concrete first, even if it's wrong. And that'll almost always tell you a way to change it, like to get you something to do. And that's, I think, true for many things in you're proving stuff. It's best to come up with something concrete that you can prove to be wrong or right, then try to sort of bubble around and use it. All right. I will see you next week. This is the end of the partners. Thank you for you. Not but we will talk about approximation.